So, good morning, everybody. Thank you to the organizers for inviting me here to give this talk. I'm very happy about being here in person. And as Sudhir said, this is kind of AGCT, and because we didn't have the last AGCT conference in person, so I mean, it's really nice to be here after 4 years. So thank you very much. Well, the title of my talk is Lower Bounds on the Maximum Number of Rational Points on Curves over Finite Fields. So I'm going to start with the setting of my talk, but many of the concepts that you see here, I mean, they came up on Monday, on Tuesday, on Wednesday, so I mean, I think that you already feel familiar with this kind of concepts. So let me precise what I mean by a curve, and of course it's going to be a nice curve, so smooth, irreducible, and all these kind of things. So let X be a projective, absolutely irreducible, a smooth curve. Defined over a finite field, FQ. So this is going to be the setting for my talk. So all the time I'm going just to say curve, but you have in mind nice curve. So what can I say about curves? Well, we can talk about the number of points of a curve defined over a finite field. So basically on Monday we talk a lot about this kind of curves. And we have like a very well-known bound that tells us an interval where this number of points of a curve can be, right? This is given by the Hasse-Weil bound. I like to add the Hasse-Weil bound that tell us that when we have such a curve, actually the number of points of the curve lies, well, let me write it like this. So the number of points of the curve minus q plus 1 is less or equal than g times the integer part of 2 square root of q. This number here is going to be called in the rest of the talk m, okay? So this, if you want, you can think about this as we have a nice interval here, right, that is centered in q plus 1, and then here you have q plus 1 plus gm, and here we have q plus 1 minus gm. So, well, I mean, as you saw the first day in Maria's talk, people have been like interested in general to know if they are curves that they are here, right? So in my talk, I'm not going to look only here, so maximal curves. I'm just going to look a little bit like here, you know? So curves with many points. I'm interested in curves with many points. So for that, I want to give another definition, another concept. Definition, first I define this quantity, NQG, that is going to be equal to the maximal number of points that a curve of genus G defined over FQ has, so X over FQ genus G. So, I mean, we clearly have a bound for this number. I mean, this is a bound. This is an upper bound for this number. But, well, I mean, as the title of my talk, I'll be interested in lower bounds, that is, like, more difficult in general. So, I define this quantity, and now, very related to this quantity, I define the defect of a curve. And this defect is going to be, like, the distance between the Hasse-Weil bound, so the maximal number of points that you can get a priori, minus the real number of points that you get of your curve. So you say this is a curve of defect, whatever the number that you get. So the defect is q plus 1 plus mg minus the number of points. So maximal curves would be curves with defect 0. You really get the bound that you want. Okay, so now if I introduced this number, it's because I'm interested in this number, right? So I mean, I want to know like what is the maximal number of points that I can get for a curve of given genus defined over a finite field of given cardinality. So one of the first results in this idea, well, I mean, maybe like a remark, let's do an easy case. What happens if the genus is 0? So if the genus is 0, so this is going to be example. If the genus is 0, then actually this interval is trivial, right? I mean, all genus curves over finite fields, you just get like a P1, you get Q plus 1 point, and then the defect is always 0. So in a trivial way, you get the maximum number of points, okay? So then we get that, and this is true for all Q, so you get this, 0 defect. Right, this maximal number of points is Q plus 1, 0 defect, nice. And now, of course, let's go with genus 1, that is slightly more complicated. I don't, can you see well here? Maybe I should switch the blackboards. Is it okay for the people that you're in the back? It's okay? Yeah? Okay. So there is this theorem by Deuring, sorry for my pronunciation, Deuring, German, Deuring? Okay. That tell us the answer for genus 1. So, well, actually, the theorem by Deuring is like a more complete theorem. This would be more like a corollary of the theorem, but well, I mean, I say that the result is by him. This is actually equal to Q plus 1 plus M, so this is a maximum, except, now I'm going to see the exception, but I mean, this is really like the maximum given by the Hasse-Weil bound. Except like in some particular cases, that is, well, I write it Q equal to P to the E greater or equal than 5 oct, and there is another condition, so I mean, it's like a weird case. M is congruent to 0 modulo P, and in this case, we don't get this equality, in which case we have that this is equal to Q plus M, so defect 1. So what is happening here? Well, basically the result by Deuring that you may know is that you can construct elliptic curves with a given trace defined over the field that you want, except maybe be careful in the supersingular case in which you may need a quadratic extension, and then it's not true. So, I mean, basically the exception that is happening here is precisely that case, the case in which you cannot find this supersingular elliptic curve, but in all other cases it works. And then the thing, of course, is that if this is like a bad supersingular curve, then you take you do -1, and then this is not supersingular, and then you can construct the elliptic curve. So, okay, instead of defect 0, you get defect 1, but nice. Okay, so we have genus 0, we have genus 1, let's go for genus 2, right? Well, I mean, genus 0 was too easy, right? Genus 1, we start to use like more deeper stuff, and now, well, genus 2 is going to be more complicated too. So, theorem, and in this case, the result is by Serre in the 83, so 40 years ago, and says the following: NQ2 is equal, and there are several possibilities, Q plus 1 plus 2M, so this would be the defect 0 case, so really like the maximum of points that you can get. Q plus QM, so defect 1. Q plus 2M minus 1, so defect 2. Or even we have like a very bad case in which we get defect 3. Okay, so this very bad case actually only happens when Q is equal to 4, so we could even ignore it. And then those cases, like somehow is good, the defect 0 case is kind of generic. So this happens if Q is different from 4, 9, and is a square, or Q is not a square, but not what is called a special. So I can give the, I'm not going to use the characterization of a special, but well, just for completeness, I'll give the meaning of a special. So a special means that P divides M, or that Q can be written in any of these shapes. But I mean, if it's not a special or it is a square different from 4 and 9, then we get if it's 0. So we really get like the maximum in the interval. If Q is non-square but a special, and an extra condition, the fractional part of this number is greater than this, then you get defect 1, and defect 2 if Q is equal to 9 or Q is non-special, no, sorry, non-square. There are many adjectives now. Non-square, special, and this inequality goes in the other direction. So we get this classification. So how does it work? The idea behind this, I mean, it's more subtle, but the main idea behind it basically is like you have the result. What did the result for genus 1? Oh, here. You have the result for elliptic curves. So now the idea is that you take two elliptic curves with a lot of points, you glue them, and glue them meaning that, of course, you can take the abelian surface that is a product, but now you have to put a polarization to make it the Jacobian of a genus 2 curve, and then you get your genus 2 curve with a lot of points. You cannot always make this glue to happen, so instead of taking two maximal elliptic curves, maybe you need one with defect 0 and one with defect 1, and then you fall down here, or maybe you may need to take two with defect 1, and then you are in this case. And I mean, this works all the time except for Q equal to 4. But I mean, of course, like this gluing, like, I mean, you have to be a little bit careful, is a lot of work. And actually, it's a lot of work because, and now this is the publicity moment, this result actually was not published. So for a long time, this result was, well, not folklore, but was like kind of one of the main results that appeared in the famous course given by Serre, first in the 83 at Collège de France, and then in the 85 in Harvard. That, I mean, many people here around, you know about this course in Harvard because Gubea was there taking notes of this course, and then those notes, the handwritten version of these notes, have been in the internet around for a long time, and people were trying to read them, and I mean, it was really difficult to understand what was written there, but I mean, the notes were great anyway. I mean, this result appeared in these notes, and now this is a publicity. We are very happy. Now the notes, they are not handwritten anymore. They are like really typed in a book here, and this is also kind of why I'm very happy about being here at CIRM, like in person, like talking about this topic, because you know how this started. Like, well, I mean, the notes started like 40 years ago, right? But then the idea about let's type it, let's make it a book, you know, that we can like easily like read it, you know, nicely, not the horrible handwritten by Gubea. So we started, and it was AGCT. So again, this conference, as Sudhir mentioned the other day, AGCT 2017. So 6 years ago now. And many people that they are here in the room, like Anna, Elena, Alina, Eve, Felipe, that I can, Felipe. You see, like many people like here in this room got involved, help us like typing like some pages of this book. So we gave to each person something like 10 pages maybe, like to type. And then, so I mean, this we edited together with Alp Basa, Christophe, that is over there, René Schoof, and myself. So we took like together like everything that was typed, and then like we reread it, we uniformized. So I mean, we really edited the thing, and then we Maximo was also involved. I'm thinking now. We gave it to Serre. Like, I mean, at some point when we had something nice, we gave it to him, and then he read it. He was very happy, even if he made a lot of changes. But he was very happy, you know. So he made some corrections. He gave his approval to get this published. And even which is nice is that he added some stuff. because, you know, like this is a course that happened in the 83, so it's like now 40 years ago. So, I mean, he added like some things. Well, I mean, in the book there are like some appendix, like say, like Everett, Osterle, and Christophe. I'm just using, by the way, the first name for the people that I already mentioned or that they are in person. For the people that I mentioned for the first time, I'm not here, I'm using the last name. So they added like some appendix to the book. So now you see there is also a little bit about the history and everything. And yeah, well, I mean, I'm going to more publicity. You can buy this book now here because this is published with the Société Mathématique de France, that the office is just here. Stefan is very involved, but you can ask him also. But can I do also a publicity that you can become a member of the Société Mathématique de France? I speak with Stefan. And well, you can buy it, and if I'm not wrong, you can buy it this week with a 50% discount. And okay, this was already like too much publicity. I come back to the to the talk and to the math. Yeah, so the funny thing about this course is that actually this course was a course that was given on Tuesday and Thursdays. So on Tuesdays, the course was related to this question. And actually the proof of this result is like many weeks of, you know, like every day, like in the course, a little bit. So, well, I mean, every Tuesday, and after several months, the students got to get like the proof of this result. So somehow, this is the part about studying this number that I introduced first for a small g. So we fix a small genus, and then we see what happens when we vary q. But then, like the second part of the book or of the course, so the Thursday talks, was about the opposite question, actually. Was the question, I fix q and I let g goes to infinity. And then what can I say? Which kind of bounds we get? And for instance, well, this is like, for me, the question that I really want to handle today is the question about a small genus, and then I let q vary. But I mean, many people also worked on the other questions. So maybe just let me say something. So, yeah, observation. Because of the Hasse-Weil bound that I wrote here, well, I mean, like this interval that is over there, we actually get that the limit when g goes to infinity of this quantity is smaller or equal than 2 square root of q. But actually there is a much better bound. Like, I mean, this is just if we use this, but we know that actually the bound is much better. So, Trimfeld, Bladut, actually this is smaller or equal than square root of q minus 1. So this is a course on Thursday that I don't want to say too much. So, I mean, you can find much more about this question in the book. I don't want to go into the details. I just want to mention that somehow the kind of tools that you use to prove this is like to really make, to consider a tower of curves. That is, this is also something that appeared, now I don't remember, sorry, in which store. On Monday, I mean, we had like these towers of curves constructions. And I'll say a little bit about it later too. Okay, so in this course, in this note, there was a question that is related with the result that we have seen now, right, for genus 0, 1, and 2. So, I mean, after doing this, Serre asked the following question. So, let me call this question 1, because there's going to be a question 2. But question 1, fix the genus is NQG at a bounded distance from the Hasse-Weil bound for all q. So, I mean, the answer to this question, at least for genus 0, is yes. I mean, like 0, you are always there. For genus 1 is, well, 1. Like, a priori is 0, but, well, sometimes things can go wrong. So, 1. For genus 2, even, let's forget about q equal to 4. Yes, 2. And what in general? Is this true? We don't know. So, we don't know, and we don't know since 40 years ago. And even worse, we don't know for g equal to 3, even. That is the next case. So we don't know. No idea. I have to say that at some moment I was like very naive, thinking, oh, I see a relation here, right? Like genus 0, you are a distance 0. Genus 1, you are a distance 1. Genus 2, you are a distance 2. Genus 3, the answer has to be 3. I suggested this to Serge at some point. He just put a face that, you cannot do that. You know, this kind of induction, no. No, we don't know. And honestly, I have to say that now even I started to think that, well, not only that it's not 3, it's even that, I mean, it's not clear at all that this answer should be yes or not. We don't know. The thing is that definitely like many people worked on this question, like during the 40 years, and even in this question more precisely for g equal to 3. I'm not even talking about the general case. For g equal to 3. Let me mention some of the results for genus 3. So, well, maybe let me say like some names of people that work on this. Van der Gier, Everett, Ibukiyama, Lauter, Mestre, Christophe, Japtop, Suzuki, Maximo, like many people here like worked on this question. We know some partial answers, but we don't really know. So the two more important, well, I don't know if the two, I don't want to offend anyone, many people work on this. But just let me mention like two results. So one result is like an explicit one. So this is by Mar, this is that. Oh, he's not that? Okay, well, this person, and Japtop in 2010, that basically they proved for some values of Q that the defect is 0. And actually this is realized, attained by twist of the Klein quartic. And you know that I like a lot the Klein quartic, so I mean this is why I decided to choose this result. With P congruent to 3, 5, or 6 modulo 7. And again, this is made with twist of the Klein quartic. So yeah, I mean, for some cases, we know that we can get the maximum. And then there is another result that I like a lot, that is by Christine. And basically, this result says that there exists always, there exists a curve of genus 3 such that the distance, this number, so the number of points of the curve minus, let me write it, upper Hasse-Weil bound is smaller or equal than 3, or the number of points minus the lower Hasse-Weil bound, and I explain what I mean by this, is smaller or equal than 3. So basically what I'm saying is that the number of points of this curve is very close to one of the streams of the interval. Like very close to here or here, by 3. But we cannot say if we are in the maximum or in the minimum. What is the problem here? Well, the strategy is similar to the one by Serge for the genus 2 case. So basically, it's take 3 elliptic curves, glue them, like try to put a nice polarization so you can get something that is a Jacobian, and then you get a curve. What is the problem? The problem is that if the curve is hyperelliptic, then great, you got it. But if the curve is non-hyperelliptic, there is actually kind of an obstruction. You know, I mean, this is because of the Torelli embedding that is like 2 to 1 when you are in the non-hyperelliptic locus. So you don't know if you get the trace of minus the trace for the curve. So you can get the maximum or the minimum. So actually, like this paper with these co-authors is just like the first part. There is a second paper coming soon in archive, so more publicity. And I mean, in that paper, we study a little bit from closer, like this asymmetry. Like, is it more probable to get curves with many points or with just a few points? That is related somehow with these questions for genus 3. But I won't say much more about it today. Okay, So, I mean, those are like some examples of questions, of results of this direction for question 1. But, well, question 1 is an open question, so we don't know, even for genus 3. This is what we got. And then, you know, so there is going to be a question 2. But let me tell you a little bit about question 2. So, I mean, after the book, after we published the book, so to celebrate the release of the book, we organized a conference. And this conference was curves or finite fields, past, present, future. And of course, we wanted to have it in person. But, you know, COVID time. So we didn't have this opportunity of having it in person. So the conference happened online. And then we wanted to do something, you know, I mean, there were a lot of online conferences at that moment. So we wanted to do something a little bit special. And what we did is that it was very convenient that Serge was in that moment in Switzerland. And I mean, I was also in Neuchâtel. So we invited Serge to come to Neuchâtel. And we made this interview to him that maybe some of you have watched in YouTube. And then we had the pleasure, I mean, to talk with him, you know, behind the interview. And then we asked about question 1. So he's not conjecturing anything. For him, this is still a question. So there is not a direction that he thinks is the yes or the no. But he asked another question, that it was like easier or weaker than question 1, but maybe was also like easier to tackle. And this question 2 is the following. Does it exist a constant that depends on the genus such that the maximal number of points of a genus G curve over FQ is greater or equal than 1 plus Q plus this for Q big enough? So what is the meaning of this question, actually, the statement? The statement is that you are asking for a curve such that the number of points is not at a constant distance of the Hasse-Weil bound, but a distance that is proportional to a square root of Q. So it's a weaker version of question 1, if you want. So if you want, a reformulation of this is instead of constant distance, at a distance of order of a square root of Q. And now this question, of course, is weaker, but it is easier, and then I can give you the answer. And the answer to this question, and is the main result in this paper with my collaborators, is yes. So this question, we can reply to it. And now I'm going to give you the proof. And actually, it's not only that I'm going to give you one proof, I'm going to give you 3 proofs. And so we managed to reply to this question in 3 different ways. So for the first, so now, I mean, the differences between the 3 different strategies. For the first one, we actually get a very good constant. So the constant is excellent, it's the best that you can get, you will see. But nothing is explicit. So which are the things here that can be explicit? Well, for Q big enough, so starting from which Q is true that you have this. So this is the first thing that can be explicit. And the second thing that can be explicit is give me the curve. Who is the curve that gives you the bound? But in this case, we cannot say anything else. We can just give you like a very good constant. Then we have a second strategy in which we give a worse constant, but at least we are going to have like some control on the Q. Not on the curve, but on Q. Explicit control on Q. And then we have a third strategy that the constant is definitely bad. We give a constant, even if it is bad. That everything is explicit. So we give the curve, or at least we give like a tower, as the towers that appeared before, that you can use to construct such a curve. So everything is explicit here. explicit construction of the curve. If I push, but good, maybe I can put this a little bit. Okay, so let me start with the first strategy. So the first strategy, strategy one. So, I mean, this is a strategy that gives like a very good constant. Actually, the proof is like 3 lines only, but you have to use like very deep, strong results. And somehow here for me, because I mean, after 40 years, let's say that nobody was able to say anything about question 1. It's not that we solved question 1, but well, question 2 is kind of getting close to it. But I mean, somehow here, I would say that the great idea was to ask question 2. So Sir just asked the right question to us, and then we were able to solve it by using like very strong results. And basically, the strong results that we use here is Kzarnak Theory. So Kzarnak Theory, that is very interesting because it's related with arithmetic statistics. That is the topic for the semester, the thematic semester here. So if you want to know more about arithmetic statistics, you can come here in May. I made also the publicity for you. So let's use, well, I mean, Kzarnak is really like a theory. I'm just going to state here like a proposition taken from this theory. That is a proposition that helps us to answer the question 2. So fix a genus greater or equal than 2. Write the number of points of your curve like 1 plus q plus a normalized trace. So this is just to get that the trace is a number between minus 2g and 2g, so it doesn't depend on q. Okay, this is the normalized trace. Then the proportion of the number of points, let me write it, well, I write it like this, and now I'll say a few words about the notation. So the number of curves with normalized trace less or equal than a given t divided by the number of such curves is equal to a given function plus an error that depends on this. So yeah, a lot of comments about this. Yes, of course. Sorry. Yeah. Thank you. Several comments. First, here I wrote the moduli space of curves of genus G, but actually you can get many other families of curves. Okay? Basically, the Kzarnak theory tells you that when you have like a nice family of curves, then the distribution of the Frobenius in this family is given by the monodromy group of the family, right? And basically, the function that I wrote here is a distribution function for the monodromy group of the family. And then you have like some error that is like, well, of this order is the error. I wrote here a prime because it's not really the curves over FQ up to FQ bar isomorphism. I really want to look at the curves up to FQ isomorphism. Because if I'm looking at the number of points, if I consider a twist, then the number of points can be different. So I really have to consider up to FQ isomorphism. But you know, you only have twists if you have extra automorphisms. So I mean, this is kind of fine. You still have like the nice properties in the family and everything. So yeah, basically this is just telling you, well, I mean, Kzarnak theory tells you the distribution of the Frobenius is the one that corresponds to this group. So basically that means this is like the distribution function is equal to this one, and then you get like some error here. So some comments, here we have control about the order, but the constant that is hidden here, we don't have any idea. I mean, if you know about it, like if there are here more people that knows about arithmetic statistics, please, let's discuss about it. I mean, I emailed like a few people, I asked, and as far as I know, the The constant here, it is not known. And somehow it's a pity, because if this constant here was explicit, then, well, you will see the proof. We could eventually also, it depends on the constant. Well, no, if it is a constant, if we know the constant here, we get the answer for question 1 in a positive way. But, well, we don't know. Okay, so this is the result. And now how this result, what did I do with my... Oh, thank you. I wasn't improvised. Yeah, so, okay, so this is the great result by Kzarnak, and now, as a corollary, we get the answer to our question 2. So, corollary for genus greater or equal than 2 and epsilon greater than 0, we can take the constant Cg equal to 2g minus epsilon. And this is the best that we can get. Because 2g would be like having a maximal curve. That is not always the case. But we make 2g minus epsilon. So that means that you can always, for every epsilon and q big enough, you can always find a curve of genus G that the number of points is within epsilon times a square root of q to the Hasse-Weil bound. So this is what the result is saying. Yeah, I mean, of course, this doesn't reply question 1, right? Because even if you take like a very, very, very small epsilon, so I mean, you are like so close, but q can be very, very big. And then epsilon square root of q is not constant, can be huge. So this is why question 2 doesn't imply question 1. But then we prove it. So what is the idea here? I think I won't write because I want to tell a little bit about the other strategies, but I'll do a picture. So basically the idea is that the distribution that we get here, if you look at the interval, here you are in minus 2g, here you are in 2g, and basically the monodromy group, well, I mean, at least if you look at curves in general, genus G, you get something like this. So you have like many curves like in the middle, let's say, and you have less curves in the streams. And somehow what we want is to say that for every epsilon, if we fix here, if q is big enough, here we are going to have at least one curve. But now the idea is that if I fix epsilon, then this is like a fixed proportion. So I just need to make q too big. So that's the cardinality of the moduli space is too big. So in such a way, this proportion here, even if I have an error, has to have at least one curve. So this is the idea. And I mean, this, you can formalize it in 3 lines actually, like writing, using the distribution function. So this is the idea. So then you need G at least 2 because the Kzarnak theory is for G greater or equal than 2. But somehow genus 1 or 0, we don't care because I mean, we know how to answer the question. Yeah. So some comments about this strategy, some remarks. Yep. The first remark is that actually this works for other families. So I mean, it's not only that you can say there is a curve such that has its number of points, means that you can take like some particular families, and those families are basically the families for which Kzarnak applies, and then you can prove that there is a curve in that family with the number of points that you want. So in particular, there are, for instance, one parameter families of hyperelliptic curves. So it's only one dimensional, and even within this family, you can prove that you have a curve with so many points. So this is the first remark. Second remark, well, no control on Q, this is bad. No control on Q or no control in the constant, whatever. So I mean, this is what make that we are not able to get something about question 1 from this strategy. So it's the thing that I already mentioned. And then remark 3 is that actually the same proof works for any point on the interval. So it's not only that you can prove that you have curves with many points, it's that you can prove that you get curves. So you take any point in the interval that you like, then you fix an epsilon, and then you can prove that for q big enough, you are going to always have curves in this interval with that number of points. So the strategy works for any point in the interval. Okay, very good. So now I move. Yes.
What do you need to know about the constant in order to get any
So I mean, I would like to know here, like for q big enough, but big enough explicit, give me a constant that I can write here.
Yeah, but what do you need to know? Do you need to know the dependency in G, the dependency in what?
So call this left-hand side minus f of t. Well, the left-hand side depends on t too. I want a constant such that this is less or equal than c divided square root of q.
It seems you should be able to get this from line back.
If you have such a constant, and you know from which q this is true, then now I don't remember all the details, but then you have the control here to prove that you have, because basically the thing is that you don't want epsilon square root of q. So you fix epsilon. So if epsilon is between 1 square root of q and 3 square root of q, you want that epsilon works for q. So you fix q0. So basically you fix q0, and now you take an epsilon that is like a constant distance, 1 divided by square root of q0. And then you want that for that epsilon works for this q0. And then in that case, you have question 1. So even I would say that the constant that you get here, I mean, is very precise. It's not just a constant, it's like, yeah, because I mean, somehow this goes to 0, right? So I mean, you could take somehow, I would say the constant that you want, and then for q big enough, this would work. So you want to have like a more precise control, not only about the constant, but also with the dependency on q. And then you could answer question 1. So yeah, it's not only the constant, it's the constant with the dependency on q.
I mean, it cannot depend that badly on q because it shouldn't have any q. Otherwise, you cannot write O of q to the, you cannot have q inside of O unconstant.
Yeah, no, that's clear. Well, eventually you could give a better dependency, right?
Yeah. I mean, maybe you have a more power saving in reality.
Yeah.
Sure, but whatever is hiding in that big O cannot possibly.
No, of course. No, yeah, yeah, but then you could give like a better.
It depends on G very badly.
Yeah, well, but G is fixed for us, so that we don't care. Yeah. Yeah, but it's a subtle. No, yeah. But let's discuss about it later. I mean, I'm really interested. So strategy 2, and this strategy 2, actually, it was very kindly suggested by Sir when he asked the question 2. And the idea, actually, that he suggested was to look at these numbers. So, well, again, there is like some notation that I will explain now. Q plus 1 minus this fq to the n divided this. So with this formula, maybe it's complicated. This number, what it is that you take a curve, genus G defined over fq, you look at all the twists, and now you do like the average of the traces of all the twists weighted with the automorphism group. Okay, so I mean, basically this is related, I mean, it's the same thing that here I have to put a prime because I only want up to FQ isomorphism. So this is the average of the normalized trace to the n. Well, no, not normalized, of the trace to the n, the power n of the trace. So one result, even if we don't use it in this first paper, but in the second one, is that we are able to prove that this is actually an integer, which a priori, I mean, we have denominators, but we managed to prove that this is an integer. And now we define the following. So for a family of curves, and again, family, you can think a little bit modular space, we consider the sum. So for all the curves in the family, you do the sum of these values. So basically what you are doing is that you are taking the family and you are doing, well, I mean, if you divide by the cardinality of the family, then you get the average of the n power of all the curves in the modular space. And the funny thing is that those numbers, for some modular spaces, in nice families, in particular for the hyperelliptic curves of genus G, we can give a formula for those expressions. So this is a theorem by Bergström, one of the collaborators from 2009, and let's say plus epsilon that we add in this paper. And it's actually that we can give a formula that is ugly, so I'm not going to write it down. But for the hyperelliptic curves, we give a formula for this, for n equal to 2, n equal to 4, n equal to 6, n equal to 8. And a priori, with some extra work and extra ideas, maybe, you would be able, a priori, to compute these expressions. And I mean, I won't go a lot on the details on this, because this is really like Jonah's specialty. But I mean, this is related with the cohomology of local systems of the modular spaces. And then you manage to give like some precise formulas. And why is this interesting? Well, this is interesting because we managed to prove theorem for G greater or equal than 2 and n even, that n even is what we got there. We define this quantity. So is the number that we could compute there, divided like the cardinality of the modular space that we are considering, plus normalizing the traces. So we define this quantity that we are able to compute. And then there exists a curve over FQ of genus G with a number of points that is bigger or equal than 1 plus Q plus this constant that we define, a square root of Q. So basically this is just to say this is an average, so you need to have a curve that have at least more or equal than that number, because it's an average. So this is a proof of this result. And the thing is that with the computations that we made, so corollary, there exists a hyperelliptic curve of genus G over FQ with the number of points greater or equal than 1 plus Q plus A square root of Q, with A well, by using those formulas, 1.3 greater or equal than 1, well, 1.3 when G greater or equal than 3 and Q greater or equal than 13. I don't have that much time, so I just write this one. I skip one. G greater or equal than 3 and q greater or equal than 11. So, I mean, these constants, well, let me say something. The genus is explicit, q is explicit. This is because this formula really depends on g and q. So we have everything. The constant here, it's bad. I mean, because somehow you want 2g, right? And I'm just writing something that is 1 point, blah, blah, blah. But I told you that this constant somehow was not that bad. And actually, this is another result. Let me use another color. We actually prove that this is another theorem. Well, I can do it here. Theorem, the limit when n goes to infinity of those numbers that we define there, when n is even, is actually equal to 2g. That is the constant that we want. So on the limit, on n, actually we get again like the best possible constant. That is 2g. We get this limit. So now I don't have, yes. This one is any curve, but then you need to know, yes. So it's any curve, but then for any curve, we don't know how to compute this. So yeah, we need hyperrealistic curves. I don't have the space, neither the time, to say something about the third strategy. The third strategy, it is explicit in the sense that we get the curve, explicit like the construction. As I said, is by using a tower of curves. So it's maybe I can just say very quick. So the idea is that we get for the constant a 4, which is not very good, again, because I mean you would like to go to 2g. And the idea is that we construct a genus 2 curve and a genus 3 curve for which you get that constant for all q. And now you do an argument, a recursive argument, that if you start with such a curve that gives you that constant for genus 2 or 3, then you know how to construct over it a curve of genus 2g and a curve of genus 2g plus 1. So now the thing is that you can reach any genus, but making these kind of jumps and starting by 2 or 3. So the work is to get these 2 curves, like, well, for every q. I mean, it's not just finding 2 curves. You have to find like families of curves. But you find those curves for genus 2 and for genus 3, and then you do like this recursive step so you can reach any genus. And in this case, the curve is explicit, like it's for q that is explicit, but then the constant is really, well, I mean, it's not that it's bad, but it's the constant that we started with. And because we start with genus 2, we actually cannot get a better constant. So it's explicit, but the constant here is really too bad. And those are the 3 strategies we use to reply question 2. And this is everything. Thank you very much.
So, you have some questions? Misha?
Could you please repeat what is the mg prime? What is prime?
Yeah, the prime is that it's only up to fq isomorphism and not fq bar, like because of the dependency of the trace.
Attends, Serge. Si, si, c'est enregistré.
Just a question about ft. What is ft? Is it an explicit formula for ft?
Yes, it's the distribution function of the monodromy group, which for some families is like totally known. I mean, it's no problem. Like in this case, for mg or 8g, it's a symplectic group actually. Matrices of size 2g by 2g symplectic matrices.
Yes. And whether this graph is the graph of ft?
This is the graph of the density function, not the distribution.
Yes, I think it should be
Yeah,
rather it's derivative, because ft is It grows. It grows.
Yeah.
Yes.
This is a
it's
cumulative
derivative.
function of this one. This is the density function, the distribution, and this is a density function, distribution function. Yes.
Thank you.
Other questions? Yes.
I'm going to put you on the spot and ask you about what's more likely, like curves with many points or with very few points. Because I know I have a guess, and I'm curious what you guys get in that preprint that you haven't
Yeah,
tested.
we get that there are more curves with many points.
Yeah, that's what I was
And
thinking.
yeah, I mean, this is actually, I mean, I don't want to say too much because I want to keep it for the conference in May, that we can give another talk. But no, I mean, I can tell you a little bit more. Like, basically, the idea is that the distribution looks like this. This is Kzarnak, more or less. So what we do is that we consider now the distribution. So basically, you consider the number of curves with trace t minus the number of curves with trace minus t. And then this number anyway goes to 0. But now you can multiply this number by a square root of q and to see what you get. And I mean, this is a distribution that we study. And yeah, we get that you get more curves with many points than with just a few points. And well, the heuristic is not very clear because there was like a previous paper for genus 3 by Christophe and other people that actually used a paper, I think, by you. And kind of you have this paper, maybe also with Kiran, about the distribution of the number of points on plane quartics. Smooth plane curves. And the thing is that it works, your heuristic, when the degree goes to infinity. But in our case, we are fixing the degree. So it shouldn't work. Yeah. But it does. So I mean, if you use the same heuristics.
So there is this heuristic that they did at the main workshop. It's after, and you know because you're one of the authors. Anyways, an AIM paper, and they have a prediction for mg to number of points on mg. And the average there is slightly bigger than q plus 1 over the whole mg. So I'm expecting more curves with many points than fewer points because you need the average to be to the right of q plus 1.
You know, I mean, for me, like, you can see the heuristics with the Bernoulli's distribution, but me, I don't see that much heuristic. I mean, I would say, and this is Christophe's argument, but like a way of saying this asymmetry is because when q is very small, if you look at the interval here, actually this number is negative. So you need to have more curves here because here you cannot have curves. So somehow this asymmetry at the beginning, you can still see it at the end, which is very nice. But I mean, I don't know if this is just an intuition or something that can be proved that it's because of that.
Other questions? I have one. What do you mean works for other families? You have to prove Kzarnak theorem for subfamilies of the moduli space, or
no, actually, like Kzarnak. Oops.
Qu'est-ce qui s'est passé?
I don't know if it was me or you, but the Kzarnak theory actually works like for families. I mean, it's like a really large theory, and it was for families for which the monodromy group can be defined. And now I don't remember exactly which are like the three things that have to satisfy. But I mean, somehow they are like very precise things, but very general. Like if you can think about a family, of course, something nice that you can define is because this family is going to satisfy. I mean, there is a monodromy group associated to it, and then this is true with the corresponding distribution function of the family. Yeah.
Thank you. No question, so we can thank the speaker again.
Thank you very much.